All right, today in chemistry, we had a video previously on Dalton's law. I took you through one of those problems, and here's a problem that I would like you to try. And this problem's much more involved than the previous flip video problem, okay? So let me take you through the problem, and then we'll have you solve for it, okay? So there's three gases: methane, carbon dioxide, and uranium hexafluoride. And those three gases are collected over water. And we know the mass of each one of these gases. And the total pressure, including the water vapor, is 6 atms. All right? Now, since these three gases are collected over water, some of that water is going to vaporize from a liquid to a gas and exert a pressure. And it's dependent upon the temperature of that mixture. So the partial pressure P of water vapor at 24 degrees Celsius, this is the temperature at which we're collecting this gas, these gases, is equal to 22.38 torrs. And I give you the conversion factor here, that 760 torrs are equal to 1 atm. Okay? Think of a game plan, some form of attack before you try this, and I'll take you through the solution right after you pause the video. All right, you paused the video. Hopefully you took a stab at this. Okay, you tried your best. Let me show you my my method here of how I'm looking at this. So I know that the three gases that we're collecting over water plus the water pressure is equal to 6 atm. So the first thing I want to do is I want to deduct the water vapor pressure from the total pressure. And that's going to leave me the pressure of these three gases. So here's what I did to sort of visualize. Okay? You've got the reaction, whatever the reactants were in this problem. These gases are escaping a vessel. Here's the vessel. And the bubbles are rising, right, because they're less dense. And they're collecting over this body of water. So this is all water, guys, right? This is all water. This is all water. And some of this water escapes the liquid phase and becomes gaseous, or a gas. Okay. So here's what I did. The problem gave me 22.38 torrs. That was the partial pressure of water vapor. I want to deduct that and find out the total pressure of these three gases that I'm trying to solve for. So the conversion factor gets me 0.02945 atms. This is the pressure of water, right? So I'm going to deduct the vapor pressure from my total pressure. And I know I'm not using sig figs here. I'm getting a little sloppy, and this is going to hurt me later on, but I'm going to run out of room here with sig figs. But I get a total pressure of 5.97. So what that means is, with water vapor taken out of this mixture, methane, CO2, and UF6 all contribute a total pressure of 5.97. So this is our new total pressure, okay, with water vapor pressure taken out. Okay. Well, I can only compare my three gases mole to mole. So if I divide the mass that we're given in the problem by the molar mass of each one of these gases, right? These are the molar masses here, right? Molar masses and that fraction in parentheses. I get my number of moles of each gas. Now remember what this tells you, right? This tells you how many moles of each gas are collected over that column of water where we're collecting these gases. Okay. If I add up the total here of all the moles, I can figure out my mole fraction, right? So the sum of all my mole numerical values here, my numerators, is equal to 6.095. And I simply take the number of moles of each gas and I divide, right? I divide by the total number of moles. And this got cut off. This is 0.6. Right? So what does this even mean, right? What does this tell you? Think about it. If you've got roughly, we'll call this 4 moles of methane, and you've got 6 moles of all three gases total in the mixture. Methane makes up 66%, I'm rounding here, of the total, which makes sense because we've got over 4 moles of methane. We got a little under 1.5 moles of CO2 and a little bit more than half a mole of UF6. So methane should, right, make up the majority of this gas mixture. Okay? So here's my methane mole fraction, right? The X means mole fraction of methane, mole fraction of CO2, etc. Okay. Take my number of moles of CO2, divide it by the total moles in the mixture, and CO2 roughly makes up 24% of that column of gas that I'm collecting. And finally, I do the same procedure here for UF6. We got a little over half a mole divided by the total. So these are our mole fractions, right? They're a percentage, right? They're a percentage. If we multiply them by 100, they give us a percentage of a number. Well, let's figure out their partial pressures. If I take the mole fraction of each gas and I multiply it by the total pressure, 5.97. Now remember, the initial pressure was 6 ATMs, but we deducted water vapor pressure, so that leaves us with 5.97. So essentially I'm finding what is 66% of this total pressure. 5.96. Okay? Let me redo that because that doesn't sound right to me. Hold on. So 0.6645 times 5.97. That gets us 3.96. I knew something was up. All right, so that's wrong, right? So 66% of this number is 3.96 ATM. So that's the pressure exerted by methane in the mixture. Let me double check my numbers here guys. 0.2424. The mole fraction of CO2 times the total pressure of 5.97. I don't know how I get these numbers here. 1.45 ATMs. Okay. And finally, the mole fraction of UF6 is 0.09321 times the total pressure, 5.97. I don't know how I got these numbers. Go figure. I get 0.556 ATM. All right, we finally get our answers here, right? So we know the partial pressures of each one of the gases in our mixture. The total pressure without water vapor is 5.96. Okay. If you didn't get this, I highly advise that you watch the video again for a second time. Hey, who knows, even a third time. Any questions that you have for class, please bring them forward, and hopefully this made some sense. If not, we'll clear this up in class. All right, guys, until next class, have a great day, and I'll see you until then. Bye.